Well, hello and welcome back to our course, ENGI307, Data Analysis and Machine Learning. So we're continuing our process of getting a nice tour of various types of machine learning methods. And so we gave an introduction. We talked about supervised learning and statistical or unsupervised learning. And so supervised learning uses a training sequence. Statistical learning tries to focus on what is a statistical way of making the decisions about whether a data element goes into one group or another. And now we're going to get into this additional area, something called the support vector machine. And this will be introducing some new techniques that we haven't seen so far with these other types of approaches. So let's go ahead and give a little bit of an introduction for what we'll cover in this module. First of all, this will be focusing on the development of linear discrimination functions, and then minimizing of misclassifications using an interesting type of phenomena here with this vector machine, support vector machine. So a little bit more detail in terms of what's in this module. We'll give an introduction, introduce what support vector machines are in general. Then we'll be talking about different type of discriminant functions, a linear discriminant function for binary classification. And so this will be one of the things that we're focusing on more than others in this course is on binary classification. So it's an either or type of a scenario is what that means. We'll then talk about linear maximal margin classifiers for linear separable data. So how can we start to create more space between different elements of what we're looking at with our data set? That would be a useful thing to conceive. We'll talk about the learning problems that are encountered with support vector machines. Then we'll get into linear and soft margin classifiers for overlapping classes and nonlinear classifiers. And finally, decomposing multi-class classification problems into binary classification tasks. And so this re-echoes what I mentioned earlier, is this focus on binary classifications is a good place to focus if we have limited types of resources that we want to be using, at least initially. So support vector machines are, quote, good learning algorithms. And so what that means is for learning algorithm design, support vector machines have the power of nonlinear functional learning with a conceptual and computational convenient characteristics of linear systems. So we're actually getting a little bit more without having to do a whole lot of work, relatively speaking. So that's a good thing. Support vector machines are effective off-the-shelf learning algorithms successfully applied in various domains. So it has a proven track record, so we can be leveraging that. That's useful. This chapter focuses on the binary classification problem, as I already mentioned, and some support vector machines. Regression analysis is a powerful technique for predictive data analysis with many applications. Regression analysis estimates the relationship between a dependent variable, that is the outcome, and the independent variable, the input features that you're looking to get an understanding and create a machine, a learning machine that can do that. So the point of concern is the linear discriminant functions. They are relatively easy to compute and are attractive candidates for initial trial classifiers unless the information suggests otherwise. The problem is finding a linear discriminant function. It is formulated as a minimizing a criterion function, that is finding a criterion classification function for the misclassification error, which we have spoken about previously. There are already developed tractable criterion functions that may be available. And so that's an encouraging point for us to consider. Well, I put in another illustration from Sugiyama to think about how we go about constructing a classifier. And you might remember that one approach is what we're trying to do is come up with a approximation for what the f of x is, how you go from the input to the output. And so here we're conceiving of an example for a discrimination function where we have this area where it correlates to 1 to 2 and to maybe some other value or going up to some larger set of areas. So that's one approach, just using a discrimination function. The other approach is a decision region and decision boundaries. So for constructing a classifier is equivalent to determining a discrimination function, decision regions, and decision boundaries. So just an illustration as we're starting to try and think of not only the theory, but figuring out how we're going to be using it with our course project work. So a linear discriminant function for n-dimensional feature space in Rn is given by Gn is equal to Wtx plus W0 equals to 0. And then we have the feature vector, the weight vector, and the bias parameters that we're seeing for the elements for that equation. The discriminant function, we can be thinking it in terms of a hyperplane H. And we'll have a couple of pictures or graphics that hopefully will give a little bit of insight of what exactly that refers to. For the discriminant function g of x, a two-category classifier has the decision rule that if the decide class 1 if g of x is greater than 0 and class 2 if g of x is less than 0. So that's a nice way of just parsing it in. So whatever way we want to be thinking of a data set, we're able to just split it up into either we have 1 or we have 2. And so that's just a way that we're starting to think about. Well, here is a simple linear classifier. So we're trying to think of this kind of an equation here. So we have the aggregation unit. So first we have g of x, it's a summation of all of these inputs with their weights. And so here we have that. And then we have an output unit. And as a result of having this kind of a linear discriminant function, we're able to come up with a y hat, an approximation of what the output should be based on the different types of features that were given in the input. So the location of a point x may be considered relative to h. We define xp as the normal projection of x onto h. And so here we have either h plus or we have h minus. Try to highlight in blue the h minus here, at least between x1 and x2, that this region to give you a perspective. And here is a projection based on the g of x function that we spoke about. So here we have some more of the supporting math for this. So we have x equals xp plus gamma w over the absolute value of w, where the w is the Euclidean norm of w, and the w over w absolute value is really not the absolute value. So double bar w double bar is a unit vector. And so doing a little bit of math, we can show this result. And the absolute value of g of x is the measure of the Euclidean distance of a point x from the decision hyperplane h. And so then we have g of x has one of three values. If it's greater than 1, it's x, then we know that it's in the hyperplane h plus. If it's 0, it's right on the hyperplane, and if it's less than 0, then it's the in for the hyperplane minus h. So we're trying to create some decision boundaries in with this kind of development, as we'll start to see. So we can have the h minus over here. We have this no man's land that's in between, and then we have the h plus. So we're taking the original vectors for x1 and x2, two possible possibilities that are there, and trying to project that into a hyperplane is what this is trying to think about. And I think the next chart will have some graphics that may help to give you a little bit of a better sense of what that's all about. For linearly separable scenarios, many hyperplanes exist to perform the separation. So we can be thinking about that. The correct answer is a hyperplane with the largest margin that minimizes the training error. And so how can we get the largest margin between samples to help us with this decision space? The goal is to select the decision boundary that is far away from both classes. A large margin of separation is expected to yield good generalization. So here we have some examples. This has a large margin separation. So the distance between H plus and H minus is large. And so this is a fairly, relatively speaking, a large value. And here is one where we have a small value. Let me go ahead and pause, and I'll come back and continue on in just a minute.